Bioelectricity is an electrical phenomenon in organisms, which is very important and universal. Electrocardiogram, electroencephalogram, and electromyograph are organ-level bioelectricity and a result of cell bioelectricity activity synthesis. Cell biology electricity is produced by the flow of some charged ions across the cell membrane, expressed as transmembrane potential or membrane potential, membrane potentials, and action potentials. Electrical potentials exist across the membranes of virtually all cells of the body. In addition, some cells, such as nerve and muscle cells, are capable of generating rapidly changing electrochemical impulses at their membranes, and these impulses are used to transmit signals along the nerve or muscle membranes. They are present essentially in all cells of the body and play a significant role in controlling the cell function. As there are concentration differences of the ions across the selectively permeable membrane, the diffusion of ions can create the membrane potentials. At a resting condition, there is an electric potential across the cell membrane with electronegativity inside the cell referring to the outside of the cell. The resting membrane potential of urine is usually about -70 mV. The related conception of resting potential. Polarization. Polarization simply means that the outside and the inside of the cell have different net charge, with the outside positive and the inside negative. Depolarization means that the membrane potential is less negative than the resting level. Repolarization. When a membrane potential that has been depolarized returns towards the resting value, it is called repolarization. Overshoot refers to a reversal of the membrane potential polarity, with the inside of the cell becoming positive relative to the outside. High polarization means that the membrane potential is more negative than the resting level. Origin of the resting potential. Concentrations of sodium, potassium, and chloride ions in the extracellular fluid and in the intracellular fluid of the typical nerve cells are listed in table. Each of these ions has 10 to 30-fold differences in concentration between the inside and outside of the cell. In particular, the sodium and chloride concentrations are lower inside the cell than outside, and that the potassium concentration is greater inside the cell. The concentration differences for sodium and potassium are established by the action of sodium-potassium pump that pumps more positive charges to the outside than to the inside, permeable to potassium than to sodium at resting condition. This differences in permeability is exceedingly important in determining the level of normal resting membrane potential. The magnitude of the resting membrane potential is determined mainly by two factors. First is differences in specific ion concentration in the intracellular and extracellular fluid. And the second one is differences in membrane permeability to the different ions, which reflect the number of open channels for the different ion in the plasma membrane. Contribution of potassium diffusion. High ratio of potassium ions inside to the outside. High permeability of the cell membrane to potassium ions at a resting condition. large amount of outward diffusion of potassium causing negative potential inside the cell. And the last one is potassium ion equilibrium potential. The potassium ion diffusion outward down the concentration gradient, creating a membrane potential with negativity inside and positivity outside. Equilibrium state, potassium ion diffusion outward down the concentration gradient, creating a membrane potential with negativity inside and positivity outside, preventing the potassium ion diffusing outward and promoting potassium ion to diffusing inward. Electrochemical driving force and potassium equilibrium potential. There are two driving forces for ions diffusion, which were caused by concentration differences and electrical potential difference across the membrane. The chemical driving force equals the electrical driving force, but their direction is reversed, and the electrochemical driving force is zero. The membrane potential in this situation is called potassium equilibrium potential. The EK primarily depends on the concentration difference across the membrane. Equilibrium potential in an equilibrium state. The electrical potential level across the cell membrane generated by the diffusion of the potassium ion that will exactly prevent the further net diffusion of potassium ion in either direction through the membrane is called equilibrium potential of potassium ion. Note that the Nernst equation allows us to predict at any given concentration gradient the cell membrane potential required to exactly counteract the tendency of the ion to move into or out of the cell. The change of the concentration gradient will change the equilibrium potential. The larger the concentration gradient, the larger the equilibrium potential. The preceding example were based on the membrane being permeable to only potassium ion at a time. When there are channels for more than one ion species in the membrane, the permeability and concentration gradient for all the ions must be considered when accounting for the membrane potential. For a given concentration gradient, the greater the membrane permeability to the ion species, the greater the contribution that the ion species will make to the membrane potential. Given the concentration gradients and the membrane permeabilities for several ion species, the potential of a membrane permeable to this species can be calculated by following equation that also take into account individual ion permeability. It is useful for calculating a membrane potential when multiple ions are present. For most cells, the potassium equilibrium potential is between -70 and -90 mV, and the sodium equilibrium potential is between 50 and 70 mV. Because of the chloride equilibrium potential is very close to the resting potential. The resting potential primarily depends on the permeability of potassium and sodium ion. Nernst equation for calculation of equilibrium potential. If the concentration gradient for any ion is known, the equilibrium potential for that ion can be calculated by means of the Nernst equation. The Nernst equation describes the equilibrium potential for any ion species. That is, the electrical potential necessary to balance a given ionic concentration gradient across the membrane so that the net flux of ion is zero. Contribution of sodium diffusion. High rate of sodium ion outside to inside. Very slight permeability of the membrane to sodium ion at resting condition. a small amount of inward diffusion of sodium ions contributing a small effect to the resting membrane potential. Okay, that's all.